Well, thank you very much for the introduction, and thank you for having me here as a keynote speaker. You know, we've been trying to do this for a couple of years now, and I had to go to Germany to actually make this work, right? That's how crazy things are. So as I said, I'm a professor at Technical of Munich, but also the chair of the MPI Forum, and so I want to take this talk a little bit and talk about the standard, where we're going, what we're doing in the standard, but also what needs to be done to make a standard like MPI work. That's not just writing the standard and putting the functionality in, there's actually more to that, and also what kind of role projects like MVAPICH play with that and how important they are to make standards like the MPI standard work. Before I go into this though, since we just heard about the OSU campus, I want to talk a little bit about, so give you a feeling of where I come from. So I was at doing the Technical of Munich in Germany, which we are in the southern part of the country, so we're right down here. The university is exactly 150 years old. We have a big celebration this year. It's also fairly large. So we have about 45 to 50,000 students. We are a pure engineering school. So there's only engineering disciplines there. There's actually a second university in Munich, which is larger. They have about 65, 70,000 students, which is a general university. Munich is a big university town and has a lot of students in there. And we are the University of Excellence. This is not just a term that we like to use. We like to use it, obviously. But there used to be a funding program in Germany where German universities could apply to the federal ministry for the title University of Excellence. Came with funding, came with staff, of course. And both universities in Munich actually became the label, so we're very proud of that. The university itself has multiple campuses. The core is downtown. There's also a large hospital, which is located downtown. We have a campus for life sciences, which actually is another term for beer brewing in this case. This is the one and only brewing department in the world, as far as I know. That's located in an old monastery just outside of Munich. And then there's the campus in Garching. There's a picture of that. This is our largest campus where most of the engineering disciplines are right now. And also we have a lot of other research institutes. Everything in gray is other research institutes as well, and blue is the university. And we're sitting right down here. This is a picture of the department. This is the Department for Math and Computer Science here. And I have to say, don't stepping too much on the toes of our wonderful hosts here, but we have one of the coolest computer science departments because we have slides. There's actually slides in the building. It's supposed to be art. We need to spend, and we build a public building, we have to spend a certain percentage on art in Germany. And instead of putting just some art up, they decided to put two parabolas, as a full parabola with two halves up. And you can actually go up on the third floor and you can slide down to the ground floor right next to the cafeteria down here, which is really convenient.
You get delayed, that's what we do.
Yeah. Yes, exactly. You can do that. You have to be upstairs though, right? Because we're on the first floor, that doesn't make sense for us. But the people on the third floor do that, yes. We also have a compute center here. This is the Leibniz Rechenzentrum, which is one of the top tier compute centers in Germany, next to Jülich in Stuttgart, with office buildings here, and then a large compute center on this side. And we're currently fielding a new machine called SuperMUC-NG, the 27 petaflop cluster using Intel OmniPath interconnect and Xeon processors. So that will be operational in the next couple of months. So this is our large compute resource, and will be the largest compute resource in Germany at this point. So there's a bit of background set where I come from, but I really want to spend the time now is to talk about the MPI standard and what it takes to write the standard, and also where we're going. So basically, the subtitle is what made MPI what it is today, and then of course also how can we continue this, and what else do we need to do to keep MPI going. Why am I doing this now? Well, I think it's a good time for this. Well, MPI just had a big anniversary. We became 25 years old. This was at a special event last year at the Euro MPI USA conference in Chicago, where some of the initial founders of MPI pulled up a session where they brought people in from all generations to talk about what happened with MPI and how it made it work. That was a really cool event. We saw the whole spectrum of that. So it's really been 25 years of the standard and how it progressed. And that's how it all started. So instead of writing my own slide, I just stole the slide that Jack Dongara gave at this particular event. And it shows kind of, because I like the picture up here. So this is kind of where MPI started. How can you not do something good in such an environment? So this is a conference in Austria, where people came together and talk about how can we combine all these various efforts that we had back then for various machines, various vendors that do all the same thing, send a message from A to B. And so instead of having something different for every single platform, the question was, can we pull it together? And actually, can we create one document, one standard that everybody could follow? And that was the idea behind MPI and how it started. Also, was the danger that it would have competing efforts, so bring everybody in one room, help to make just one effort out of that. And it was the right time at this point. And so Jack and Gar knows that they worked on Scala-Pack at this time, so they needed to develop software that had to have this capability. And that's how the MPI standard really got started. From there, MPI kept growing. So I took the slide from you probably remember this, Adam, that Adam put a slide together after MPI 3.0 to kind of show the trajectory of the standard. It started with 228 pages. We're now at over 800 pages, so everybody knows they print out the MPI standard. It's gotten quite a thick book. But it has a lot of interesting functionality, and actually the size is not as daunting as it looks like, because a lot of stuff is really put in to be orthogonal and to be consistent and so on. I think that's actually a good thing in this case. But you see the progression between the major versions, between 1 and 2 and 2 and 3. There has been quite an additional functionality, and this also means, of course, adding pages to that. So today I think MPI is alive and kicking. As it is the most dominant standard inside of HPC for programming. It's used by basically all HPC applications. There's very few who don't. And those who don't typically use a runtime system that is then can build on top of MPI, because MPI is the portability layer for the runtime system. And also, if you look at any procurement in the HPC area, this is one of the requirements that everybody puts on the vendors, provide us an MPI that works. And there's another example. I was involved in a community project called OMPX, which actually dealt with the additions to OpenMPI for exascale. That was part of the US ECP project, the exascale computing project. And at that point, we did a survey among all exascale projects in the US. What is the usage of MPI? And it came out that basically all applications use MPI. 93% basically all but one application expected to use MPI at exascale, and also 57 of the middleware projects use MPI. And that's, I think, particularly remarkable, because middleware, a lot of the projects were single node projects. They're very localized, so it's not that the rest doesn't use it, but the rest is at a single node. But a lot of these projects, and as soon as they go out of node, again, it did rely on MPI. And also, when you look at this, we have a very stable community participation. In the MPI Forum, in the process of defining the MPI standard. Vendors are still very much active. There's a very strong open source community, for the MVAPICH team. There's a very strong tools community which participates as well. So not just building the runtime abstraction and making MPI available, but also building the tools for that, so we know that we have correct code, that we have fast code. And also, if you go to events like BOFs at SC or ISC, we get a very strong participation by the community, a lot of feedback. So there's a lot of interest. So I think MPI is definitely still alive and working well for the HPC community. And there's also, it's a part of many CS and CSE curricula. I myself, sometimes I started on the academic side. I got to teach MPI for the first time this last semester, and it was actually kind of interesting to see how students react to that, and how well they received it and how interested they are in this topic. So the question is now, what made this happen? So why did MPI become this kind of dominating HPC standard? So of course, the first thing was start this whole thing at the right time, right? Targeting the important problem that everybody cared about at the right time when things was right. And I just want to, without saying much, I just want to put up the slide from Jack and Gar again, because that's basically what it was. Right? There was a time where these machines became more interesting, where these machines grew in the deployments. There was a need to do message passing. Everybody did it somehow, but not quite the same. So there was the right time to jump in, and for some people that had a vision for that to actually go in and say, we need to do something here so we can keep these machines compatible, we can keep the software compatible. Because we had this message passing was in the air. And also there was really identified there were different efforts around the country. So that's the right time to actually start a standardization project like that. And that's really what kicked it off. So that was the first part. And the second part, of course, is to get the right functionality down, right? So make sure that what you're providing is actually fitting the needs of the users. And it's also put in a way that you can actually make use of it in an easy way. And so I think the MPI concept, in particular the ones we look at the very early standards, were very conducive to that. It's a very minimal set of functions that you needed to use to write a program. Basically, you can write a program with 6 functions. You have init, finalize, get rank, get size, and then send and receive. If you know these 6 functions, you can write an MPI program. Probably not the most efficient one, but you can write a program, right? So the idea of just having an explicit communication, the send and the receive on the matching sides, I think that was a very strong thing to do. But then there's a lot of additional complementary concepts that you could add in addition to that, that not necessarily have to know everything ahead of time. It's also why I don't think these 800 pages are that daunting, because you don't need to know the 800 pages. You need to know what you want to do for your particular code. And so one thing was also in the very beginning is the idea of non-blocking, so can you overlap communication and computation. And this was kept very much parallel to the initial set of functions, so you didn't have to learn a new concept. It was just the idea of having every function blocking and non-blocking, or synchronous and asynchronous. And so this matching really helped, and the idea of this return, this completion object, the MPI request object, having that, I think was also very, very straightforward. And also that was carried through the whole standard. So I really, what I'm kind of get to is, there's really a couple of concepts that really go across the whole standard, and having these consistent and go across the standard really helped, and also helps in understanding what works in the standard. The other thing was the addition of collectives, that yes, you could implement collectives yourself if you wanted to, but this wouldn't be efficient, and so having a couple of primitives of things you need all the time, and define it in a way that you can actually write optimized implementation, I think helped a lot. There was all directions of fan in, fan out, and in-out operations, and also the reduction operations. So we all know these very well because they were there from the very beginning on. And then people started playing with persistence, and that's something I think that was in the beginning put in for point-to-point, but I think it was left open there because I think this was actually very useful for other parts as well. And you'll see in a second they'll be reviving this, and we're bringing it back and making it even more orthogonal in the whole standard with the new efforts. But there's persistence for point-to-point where you can say, this is an operation I'm doing over and over again, so just remember that, optimize for it, and I'm just going to kick off the operation when needed. But again, very, very similar in matching the operations here. As again, these things happen just in multiple versions, but with a very similar semantics, so you don't have to learn concepts over and over. You can just use the one part. The other one is, as I already mentioned, there's a lot of design concepts which are kept throughout the standard, which are very consistent, which again I think make a good standard. So people that initially designed, they really had the vision to put this in the right way. Again, with the goal of being consistent, which makes it easy to learn and also hopefully easier to implement. Communication concepts, the idea of communicators is one of that. That really goes through the whole standard and touches every single part in the standard. Everything is derived of a communicator. You know how to handle that. You know how to build these groups from the communicators, and you can derive the rest from that. The data types is another piece which is almost orthogonal in the whole standard. Everybody uses data types. There's a separate set of functionality to create data types if you want to have your custom data types or use the predefined ones. Again, this goes across the whole standard and it's used everywhere. And then the other thing is the orthogonality, which you already mentioned, that if you have these send-receive operations, those appear in the standard multiple times, but in a very consistent way, and then they're crossed with the idea of having blocking, non-blocking, persistent communication. And I think that makes it very easy to learn, because you know if you want to go from a blocking to a non-blocking one, you know what the syntax is, what to look up for without having to learn a new concept. Yes, this increases the number of functions, and that's why the standard gets so big, but you don't even have to remember every single function, because you can actually deduce the names, you can deduce the functionality. You put an I in front of it, it becomes a non-blocking, for example. If you put a start behind it, it becomes a persistent operation. So this one, we get some ease of use. Doesn't make the life of the implementers very much easier. They always complain that they have to support and test many more functions than that, but I think for the users it's actually a plus to have all these functions. And then the other thing which was decided early on is to keep it independent of the runtime system. So we notice in the MPI standard there's never anything about how MPI interacts with the runtime system, how it gets launched, how it, what MPI exec or MPI run had for parameters that's all put externally on. And it was done very much on purpose to make it easier portable, so you actually can take an MPI and put it on different systems. And so this is sometimes seen as a little bit of a weakness, but on the other hand, it also has the big advantage of portability. It's why we've seen MPI on so many more systems. I think if we would have had nailed that down, I think vendors would have balked probably early on and would have gone a different way. That was the initial days, so that was kind of where MPI started, some of the functionality we had. And since then, a lot of other things got added. Non-blocking collectives was one that was an obvious gap. We had the blocking and non-blocking point-to-point. We had blocking collectives, but there was no non-blocking collective because it was very difficult to implement in the early days. And so this got added on later on. But again, with the idea of being orthogonal, you can basically just guess what the non-blocking operations are for the collectors, and you can guess their prototypes and their parameters, because it's the same thing as the collectors, just with the request object at the end. And we also kept the weight and test semantics for to be used for point-to-point. But again, same concepts, just replicating it across the multiple ways to do communication. Some really new stuff that got added in MPI 3 in this case is neighborhood collectors, which I think is a very interesting concept and not very used much. But the idea is you can actually specify a collective operation not across the whole communicator, not across the whole partition of the program, but just for your neighborhood. So basically, you think about a stencil code. You can do a reduction on a stencil without having to specify it across the whole COM world. And with that, you can be scalable, implementations can be much more localized, and you can have much more efficient communication. And you're basically telling MPI your localized communication patterns, which again allows optimizations, allows MPIs to do implementation, clever things in governance. I think that's a very strong concept that has been added recently. It's available in almost all implementations these days, but I think it hasn't been used as much as it could, and I think there could be a lot of potential in there. Remote memory access is also one of these things that was added as kind of the idea of having the ability to one-sided communication to be a put or get to a remote memory location that was added in 2. It was actually not one of the best parts of the MPI standard because it had some problems early on. It was probably standardized a little bit too quickly. I think everybody realizes that, and so it was revamped and improved in MPI 3.0. And I think the one we have right now, the versions, I think are much more palatable, and actually we've seen some good performance nowadays in the modern MPI implementations that we can do one-sided communication. You can do some really clever tricks, particularly for modern runtime systems, of having faster communication by using this one-sided. In particular, since implementations on systems like InfiniBand support this in hardware. If you have this not supported in hardware, the ability to write something in another memory, you have to emulate it, and it's probably not as fast. But modern networks actually do that. And so this is actually, I think, from that point of view, a very interesting direction as well, particularly if you develop libraries and develop low-level the layers that use MPI. MPIO as well, so this is an addition to the MPIO in MPI 2, the thing that has been very successful. And the last thing I want to stress, since I personally come from the tools side, this is how I started a lot of my research career working on performance tools, debugging tools. I think the tool support in MPI is really something that's unique, and that's served kind of as a role model for a lot of other standards. Even MPI 1, there used to be a profiling interface already that allows you to intercept every call that was made, to write tools for that are portable that you can bring across systems. That was really unique and unheard of at this point. And so other standards now are catching up with that. So there's a tools interface for OpenMP coming up with the newest version, for example, that kind of took some of the ideas of MPI and pushed them forward. So you can write tools that go across all OpenMP implementations. Here we can do this for the MPI part for a long time. And with MPI 3, we actually added the MPI tool information interface, which gives you internal information. And I'll come back to a little bit later on that, in particular the role that MVAPICH played in making these interfaces working and actually showing the usefulness of them. So that's what we have so far. Of course, we didn't stop there. I want to spend some time now saying what's coming up. We're actually planning on a release of MPI 4 rather sooner than later. I'm going to show the timeline in a second. But this is coming up, and these are features you will see in implementations like MVAPICH, and also for the MVAPICH team. You probably get ready for implementing those. Some of them are actually going to be quite fun to implement, I imagine. So So some of those things that are already in the standard that are ratified, that just haven't been put in a standardized version, but those have gone through the MPI Forum, who works on the standardization of these concepts. Those have been blessed by the forum, and they're in the what we call the golden copy of the standard. So for one, you will see assertions for message traffic, which I think is going to be quite useful if you know exactly what your communication pattern is and you want to optimize for a particular scenario. So you can, for example, state that your application on a particular communicator doesn't use wildcards, that you don't care about whether messages overtake each other. All these things that are guaranteed in the standard, but you may not use the features. You can now tell MPI you don't need that. And an MPI implementation can start using these hints and optimize on that. So for example, if you don't have wildcards, the queue management gets much simpler.
That's something that we really useful, especially for like tag matching. If you want to offload tag matching,
exactly.
This is going to significantly simplify the implementation.
Right. So this was actually driven by some of the hardware vendors who want to do exactly that. Yeah. And so you will still have all the wildcard, all the functionality in your code, but you can now testify to MPI, I don't want to use it, and with that you may get much significantly improved performance. So that was the traffic optimization, and said, but this is really an implementation opportunity here where you can an optimized implementation, particularly once it tries out more and more things, like MVAPICH is a very good example for this, really has a chance to make use of that. Kind of associated with that indirectly is there's going to be a small change. We're changing how info keys propagate in community duplication. This is made to make these assertions the right way and allow it to do it in a safe way, because those are also on the info key part. So we're not propagating them by default anymore, but there's a special iDupe with info now, which allows you to propagate what we had before. And with that, you can control the properties better on what's attached to the communicator. You have more choice of doing that. And with that, you can set the right assertions here for these kind of features. There's and also attached with that is what does it mean to actually query the MPI Info Object on the communicator. That was ambiguous in the standard what it actually meant. So if you're using this function of querying the info object, this maybe worth a look, because it was unclear. Does it provide you what's actually set, or what is set? Basically, what did the MPI implementation take of the info object, the hints that you provide, what is actually making use of, versus what you actually initially gave the implementation. It's a very subtle difference, but if you want to understand what the MPI actually did with the information, this is now clarified. You can query now which hints were actually taken and actually make a difference on the implementation, or whether it's something you just provided but the MPI implementation ignored. Another feature that has already been passed with deprecating send cancel, I think that has been a thorn on the side of many implementers. So you can no longer cancel send, which is kind of useless anyway from where things are written, but this is deprecated now. And then there's a couple small fixes in the MPI tool information interface. So that's basically what has been voted on and put in the standard as of now. This is not, this is rather small things, but I think this can be a huge potential of that. But before we get to MPI 4.0, there's a couple more features that are going to come up, and these I think the more interesting big ticket items. The biggest one is probably this. So this is anticipated. This is in the voting process right now. I personally expect this to go through. We'll see what the forum decides to do, but so far I have not heard anybody who's objecting against that. So we talked about before that we have these blocking, non-blocking persistent for point-to-point. And then we had the blocking collectives, we added the non-blocking collectives, and now this is the next thing, we're adding the persistent collectives as well. Again, making things more orthogonal, having these concepts really go through all modes of communication. So this is the last piece that was missing, the persistent collective. The idea is if you do a collective over and over, you can set this up once ahead of time in your code. You can say, I'm using this collective multiple times, and then you can just kick it off and say, now do the collective with all the parameters that you have set before. And so this is very similar to what happens in the point-to-point. And the idea, of course, you can do optimization options now. So an implementation can now say it's worth optimizing this particular collective, set up special trees, set up special communication channels, set up particular hardware features, reserve hardware features for these collectives. So again, there's a lot of performance potential in there. But there's a second point, and that's a little bit of a subtle one. That's why I wanted to explicitly stress it. It actually changes a little bit the semantics of the collectors. The collectors, if you're familiar with that, you have to order in the right way. So you have to have, these collectors have to be ordered across in a communicator, so you do them in the same order, because you have to know which one matches together. And this is still the case here for setting up the collector. So this, in order to make sure you know which collectors match together, you have to set them up in the right order and put this together. Once you get to starting of that, this connection has been made. And so you're no longer bound on the order of how you kick them off. And that actually opens up new algorithmic opportunities. This was actually put in place, or was suggested by people who are using task-based languages who wanted to do collectives in tasks. Because the tasks are out of your control when they get scheduled. So we're going to put this kickoff command in a task. You couldn't do this if there would be this constraint of having the same order because you don't have control over the order. Now you set up this collective outside of the task system in the beginning, and then you can kick these things off in the task. You still need to ensure that this gets kicked off eventually on all processes, but it doesn't have to be in the same order anymore, which really opens up the door to new algorithmic optimizations. The other big thing we're doing is we're looking at better defining what it means to have a fault in an MPI program. As you're aware of, if you have a fault now, the whole MPI job dies. That's kind of the default scenario. And this is very much, there's very little to contain anything that goes wrong. And so this is being changed to the point that we don't require MPI to fail anymore. This is still an option, of course, if that's what the implementation wants to do. But we're giving implementations, again, to be better and be more specific of what they do. Now implementation can limit failures to communicators, can report these failures on particular communicators. And also we had this feature in there, feature quote unquote, if you saw a failure on a general, not bound to communicator type operation, you would have to basically raise the failure on COM world, and with that bring the whole application down. We're actually changing this to raise the failure on COM self, so very much localized now. And with that, you give the rest of the implementation a chance to stay alive if it can. So this is actually backwards incompatible. It's one of the very few times the forum decided to do something that's not backwards compatible. This is probably a very subtle point that very few applications use. But I think it's going to be a huge help. And so we now be able to contain faults to very small parts of your application. And you can write fault-tolerant abstractness on top of that now. And we can also use this as the basis of making further fault tolerance progress within the MPI standard. I see this as the first step to providing full fault tolerance in the standard, and that will be what we have in MPI 4.0 at the least. And there's also some optimizations in the RMA operations that go in the voting process right now to have non-blocking constructors and destructors. Again, it's the idea of if you have anything that's blocking, we want to make non-blocking versions of that be orthogonal. Particularly non-blocking things for runtime systems are very useful. If you implement something, you want to have things non-blocking as much as possible. So these are the features that are in the voting process that are written by their full tickets. If you're interested in them, I can point you to the tickets. These are from the semantics pretty much tied down, and we're only tweaking the last couple of bits. And then these are kind of the other tickets which are still under discussion. They're still being developed, but there's a good chance they will end up in MPI 4.0. So they're far long enough that they will be voted on in the next couple of meetings, and there's a good chance that these make it in 2, but those are a little bit still under discussion. So for one, we're talking about adding to the MPI-T interface, the MPI tool information interface, to add events to that, so you can get callbacks to certain things that happen in the standard. And so we're providing busy tracing capabilities, and I'll go into that a little bit more when I talk about tools towards the end of the talk. There is clarification going on in the standard uses the word process for when we talk about MPI process, and it was never really clear what that really meant. Originally, we always had the thing in our head that MPI process equals OS process, which actually was never spelled out and was never intended to be spelled out. An MPI process, a separate entity, actually has nothing to do with an OS process. And so we're going through the whole standard, all 800 pages, to clarify this every single time the word process appears in the standard. It's a huge work that the working group is doing on that one. But it will help make the standard much more clear and much more precise. And in particular, we're going to enable MPI implementations that don't have this mapping. There are some implementations which take an MPI process and map them to a thread. And that's actually allowed based on the current standard, even though a lot of applications that we have these days would fail. But in this case, we want to make this explicit that this is allowed. That gives implementations even more flexibility to implement it. Again, it doesn't have to be, but they can use it this way. Another thing in the discussion is large count support. So how can we support communication of things that are larger than, have a larger count than 32-bit? Sounds crazy to have these large messages, but actually there are applications which use that actually came to us and say we need this kind of feature for particular codes, and also particularly for the I/O side. Having files larger than the 32-bit count is something that's very much used in a lot of scientific applications. There are tricks right now to get around that, but playing with data types, but it's very inconvenient, and so we're trying to put this in. The problem is, if you just change the type of the count, we actually make the interface not backwards compatible. We don't want to break that, and so we're probably going to add additional large count functions into that will give you the 32-bit and the 64-bit options at the same time, and then you can pick which ones we're going to use in your application. Imagine over time that really takes on with some point which we would deprecate the old functions, but that's probably several versions down the road. The other big thing that is still being discussed is the handling of native data types. That was triggered by a discussion on how do we support FP16. Some of the modern processors, in particular the system for the post-K system in Japan, is using FP16s. The reason is obvious. We want to support deep learning applications, AI applications, neural networks, which will often rely on these smaller floating point operations. So how can we add that? The initial idea was let's just add another type to MPI, but then the discussion kind of grew from that. So what happens with the next type? Do we add a type every single time, make it the standard more complicated? So we're working on a general solution that allows us to take types defined in host languages in C and C++ as those standards evolve automatically into MPI with a kind of standardized naming scheme. So that you can use other types that C, C++, or Fortran define and use them directly in MPI without having to change anything. And then the other thing is there's more efforts in progress to strengthen the orthogonality I was talking about. There's more synchronous operations in the standard which are blocking, particularly on the communicator side and some of the allocation side. Should we provide asynchronous or perhaps even persistent operations for that as well? So we're going through the standard and trying to fill out these missing gaps in the orthogonality as well. So this is all active work, and there's a good chance that the majority of this will end up in MPI 4 as well. So you see there's going to be a huge jump in functionality again between MPI 3 and MPI 4, which is kind of the intention of that, and MPI 3 has been a couple of years now. So I think it's the right time to push this forward. Here's the timeline that we're talking about. This is tentative. This is what the MPI Forum would like to do. If it's going to happen this way or not, we will see. But the idea is we're going to publish a draft standard. That's something new in the MPI Forum. We added this a couple meetings ago that we want to do a yearly draft standard for everything that has passed but not been put in an official version. We're going to target SC18 for that, so you can see everything that has been passed at this time in documented that we can get out for community feedback. We're going to do the same thing in SC19, and this one will basically be the better standard for MPI 4.0. So we basically have a year left to add functionality to what will be in MPI 4.0, and then we're going to tie it down. There's a certain process that we have in the forum on how to release the standards. We'll kick it off at that time. This would mean that basically you would have a standard of MPI 4.0 before ISC 2020, so about the summertime of 2020, where you can expect an MPI 4.0 standard. The features you'll see probably at SC19 already in the draft standard, to kind of get prepared for that, and also give the implementations to the chance to catch up early with that as well. Okay, so that's kind of on the functionality part, kind of an idea where we're going with the standard. So back to this, so we targeted the problem at the right time, we have the functionality, we're driving the functionality, we're expanding it, making it more orthogonal, but there's a couple of other points you need to really make the standard work. And the one big thing is you need a dedicated and open team to work with that. This is a lot of work and get right. And kind of to show you what this is the list of participants that have been at the physical face-to-face meetings over the MPI standards. This is not the people who have been in the working groups or did implementations or provided papers on that. This is literally just the people that physically showed up at the meetings. So you can see it's a huge list already, and if you would add the other ones, there's no chance to fit this on the slide anymore. And so this whole thing came together. These people then formed the MPI Forum. So for those of you who are familiar with the forum works, this is basically the standardization body, as DK said in the beginning, that kind of drives the standardization, the discussions about the features of MPI, discusses new directions, oversees the correctness, and we're also looking a lot at the quality of the standard. There's a lot of discussions about subtle semantics in there and how to make sure that these things are precise and accurate. And also we represent the MPI to the community, so we're holding BOFs events and tutorials and things like this. A little bit different to most standardization bodies, this is actually an open membership model, so if you want to be part of the MPI Forum, you can just sign up to be a member of the MPI Forum, you don't have to pay any dues or anything. Any organization is welcome to participate. We have both working groups and the actual MPI Forum, the face-to-face meetings. Working groups are virtual, so you can just basically join the mailing list, dial in and into the phone conferences and participate and help us with designing the right one. We also have physical meetings 4 times a year. Typically we have 3 in the US and 1 outside of the US with the Euro MPI conference, wherever that will be. This year it's in Barcelona in September, so we're holding the non-US meeting in Barcelona in the middle of September. And then between the working group. What's the kickoff is how this works, is we're doing the voting rights based on attendance. So in order to be a member, you just have to join the activities. If you want to be a voting member, you have to show up to the face-to-face meetings a couple times. It's 2 times out of the last 3 meetings, and if you're there often enough, you become eligible to vote. So you basically want to prevent people just coming in and voting something down. You have to have a history basically of participating, and that has worked very well so far without having just to clamp down to a particular membership model. And also it's based on the organization, not the individual. So if you have an organization of multiple people, you can send different people every single time, which also has worked very well. So if you're interested in that, to take a look at the webpage, and then here in particular we list the working groups. These are the currently active working groups and their chair. And I don't want to go through this, but I'll keep it in the slides so you can look at that afterwards. If you're interested in any of the topics, just approach the people directly. They're very open to getting new people in, to have people participate in the working groups and add to the discussions. And I said the working groups themselves are mostly virtual, so you can just dial in, join a WebEx or something like this, and help the discussions. So this is the team. I think that's really important. There's a lot of volunteer work going into the standard. There's a lot of hours being spent on that, on the user side, on the implementer side, and then also people actually writing the text. But also this has to be driven by a very dedicated process. We have actually very strict rules on how to make this work. And the big thing is we want to do this on consensus. We don't want to just push new standards or new features through. The idea is to only push things through that have been agreed upon in the community. So there's a very defined process on how things get added to the standard. And so the first thing is you typically bring this up through a working group. So that's why I said if you're interested in doing something, join a working group, discuss your ideas with the working group, and kind of make it known. And yeah, there's probably a lot of good feedback on what will work there. Then the idea is you create a preliminary proposal, and then the idea is the socialization of this idea. This cannot be underestimated, right? If you bring just a proposal in front of a large group, everybody will be skeptical. So you need to start socializing what's the need, why we want to do this, why is it important, what's the impact on the implementation, what's the impact on the applications. And this typically is done by the working group with the help of the working group, and that will be then the basis to create a full proposal. Once you have a full proposal, it goes back to the full forum, and there we actually have a very strict process, and it takes actually a long time to get something. You actually need 3 physical meetings to get something in the MPI standard. That sounds like a crazy overkill, but it's actually done very much on purpose. There's supposed to be time in between to think about that, whether it's the right thing, whether we missed something, you have time to go back to talk with the organization, whether it's the right thing, whether it fits the implementation. So we do 1 reading, where you actually read the text in front of the forum. And when I joined the forum, I thought, well, this is stupid. Everybody can read it themselves, right? it's actually amazing how many things you find if someone stands up in front of a room and reads a text and everybody reads along on the overhead projector. You find a lot of subtle problems, you find a lot of grammar problems, you find a lot of inconsistencies if like 20, 30 people read the text with you aloud. It's a very interesting process. I've never seen anything like this before. It's actually worth seeing one time because it's amazing. And then there are 2 votes, and these votes have to be passed with a 3/4 majority. That's the idea of the consensus. And typically, most votes are unanimous. By the time it comes to a vote, it has gone through so many iterations that people kind of agreed with it. I've seen 1 or 2 votes where one person was against it and one person abstained. If it's more than that, everybody else will say, wait a minute, if there are 2 people objecting or that, something must be wrong. We have to go back to the drawing board and iron out these things before you bring it up to a vote. So that works actually fairly well. It's slow, but I think the result is a more precise standard that really reflects of what we need and that's consistent with the rest of the document. And then so that once enough topics are completed, that's the process we're getting to with MPI4 at this point. We're going to work with publishing a new standard, is putting it together, the whole document, doing quality control on the document, and actually releasing it on the website as a new standard. Okay, so this is the other part. So we're talking about functionality. We have the functionality. We have an open team to work on this so that they can grow and has people coming in as needed. That consensus-driven process. But the last part, and don't think that can be stated strongly enough. I think this is what I stress a little bit more now is you need reference implementations to make this work. You have to have projects that actually take the standard and implement, because if you just have it in a standard and nobody implements it, it's not worth anything. But you need to get it in the hand of the users. And these open source projects that we have, which include the MVAPICH project, but also MPICH, OpenMPI, MPC, projects like this, that make the code available, that work with the community, that implement is, I think, crucial to make standards like this work. And we are in the lucky situation in MPI, we have multiple of these reference implementations. So we have MPICH and OpenMPI that are often used as cores for these things. We have projects like MVAPICH, which I think is particularly of interest because it's university-based, and they give a lot more ways to experiment things and have students work on that and try things out that not necessarily a company could do because it's not worth the company, but could lead to interesting results if we do it on the student side. It has its own character as an MPICH. And then things like MPC. So MPC is one of those implementations that do what I said before of having one MPI process equal one thread. And so they're trying on a different route. I think they're also they found some new things in the standard that we weren't aware before because they're doing something new in a new direction. All these things is public, which I think is very important, which enables the engagement. I mean, projects like MVAPICH have been used by many other researchers, have been downloaded, have been extended. Things have been fed back into the standard. This only works if this thing is open and can actually be worked with. And it encourages fund contributions. So we have several students also working on MPICH and MVAPICH because it's easy accessible and there is a good way to feed it back. And I think that helps the community a lot as well. So this has the advantage that, of course, you have competition, which is always good for performance. The more people you have working on this, the more the implementations will be pushed. And you can kind of see this particular between the two labs, the DOE labs, which run MPICH and OpenMPI. They're always talking about who has the 5 cycles shorter critical path, which is kind of fun to see. On the production side, having more than one implementation helps mitigate risk. So in particular, so when I was at Livermore still, we always had OpenMPI and MVAPICH on the systems at the same time. One was the preferred solution, in our case, MVAPICH. But if something was wrong, we could switch to OpenMPI. And other labs did exactly the other way around. They had OpenMPI. If something was wrong, they could switch to they would switch to MVAPICH. And so this is kind of a useful thing to do the risk mitigation. And then also you can, because you have it open source, you can modify it for your own purposes. You can make additions to that. You can make patches to that. And the other thing is this also helped really drive the implementations. And so this is the MPI 3.1 implementation with the new features as of November 2015. So that's a couple months after MPI 3.1 came out. And you see there's a lot of features already implemented. And if you look at MVAPICH, it had almost the complete thing already back then. And now the last piece was filled in as well. And so having these implementations come out quickly after the standard is passed to make sure we get the new features in the hand of the users and not they have to wait 5 years before this thing actually gets implemented, like we see with other standards sometimes, is really critical in that as well. And so we had a really good success working with a lot of the vendors and implementers on making this work, and I think that helped the standard quite a bit as well. And I want to take a particular example out as well. I want to take a look at the tools interface, as I mentioned before, because that had a couple of extra features which made it particularly important to have groups like MVAPICH jump in and implement this early on. So for those of you who are familiar with that, the MPI tool information interface that was added in MPI 3, the idea is it gives you introspection into the MPI layer. So things that you cannot see from the API side, you cannot see by simply intercepting send and receive calls or other communication calls. It gives you a standardized way to access this information through tools, and with that we can get implementation-specific things out of there. And so we get these internal information, and we split this up into configuration, control information, and then performance information, and also debugging information. You can access that. Things that you wouldn't normally see, or you would have to read documentation, or you would have to instrument the code manually for. The MPI information can get you to that, and this whole thing is standardized. The idea is we wanted to add to the very successful pre-MPI interface, so we added basically a whole tools chapter and added the MPI 3 interface into the MPI T interface into MPI 3. This was, by the way, the single largest addition of function calls in the MPI 3. There's actually surprisingly a lot of function calls needed to make this work. So a lot of the extension of the between MPI 2 and 3 was actually due to this tools interface. And so with that interface came a particular challenge, and that's kind of where a lot of the problems came in. We didn't want to specify which variables existed. That was tried before, so you have to provide following information, and that never worked because the vendor said, I don't have this information, I don't want to give you this information, that will slow down my code. So we could never agree on a set of functionality that is provided. And so we did it the other way around and said, you tell us what you want to provide, we as a tool figure this out, and then we could use this information, just give us some meta information for that. And so by default, the MPI is actually, it's okay not to provide anything, of course that's not preferred, but it's allowed in implementation that we made as the kind of a sacrifice we had to make to get this into the standard. Compare this to hardware counters on processors, right? If you run PAPI in a system, technically PAPI can always say there are no counters available in the system. The PAPI counters are different on every system, and the same thing is here as well. So things can change between implementations, between different versions of the library, between different executions of the same library. And so, yeah.
Actually, I have a quick question.
Yeah.
Now, from a tools implementer's perspective, let's say OpenMPI can say that the performance variable for sending out the number of bytes is OMPI num bytes sent. And perhaps you can send something else. Is there any, so from implementer's perspective, that's a major challenge, right, to figure out what exactly to query. Is there any idea to standardize that, saying that, hey, if you are for byte set or byte receiver, at least for some common set of PVARs to have some standard variable names?
Yes. So that's the hope that I personally have, that we can do this, right? That once we have enough experience with what MPI T can do and what different implementations provide, that we then sit down and say, oh, this matches up, let's just define a common name for this. I have my doubts that will ever go into the MPI standard, because there will be pushback from that. But you could think about a side document like we have in the message queue document or the MPIR document that have a separate document that maps this up. Or you have something like PAPI. Right? PAPI has the L2 cache counter, which then would map to the division in native one, so you could do something like this as well. That's kind of where I hope we would go eventually. But I think it's still too young to really know what else can do. I think people haven't played with that enough. So I think give it another 3-4 years, and I think we should be ready to do that. But that's exactly the question. So you have this chicken and egg problem. So you need to be able to have the experience to know what you want, but on the other hand, you need to have the implementers provide that and guess what people will want to use. It's exactly the question, right? And so how do you do this? And the performance values is one thing. So we need to query these ones, and we provide these names, descriptions, and metadata. But is it the right thing? And so here's a sketch of that. So to those of you not familiar with the MPI tools information interface, you have a user requesting information. You have the implementation. You split up your tool into 2 parts. You do a setup. We query all the variables, you get the information back. After you get it back, you can pick a particular variable, and then you have a counter, you measure and you stop the counter and you read out the counter values. That's kind of a high-level sketch of how this works. The big thing is you have just two things. You have the setup and you have the measurement phase. And so the question was, how could we get the implementers to actually provide and put these first performance variables in so we can actually start playing with that, since it's not necessarily required to provide a compliant standard. And the MVAPICH project was actually one of the first ones to provide some information on that. They actually worked with us at Livermore very early on. We had some of DK students at Livermore to actually work on that. It's already in 2014, so that's actually a year before the standard was made fully public. We had the basic ideas already, but already a year before we started seeing some of these variables in MVAPICH, and we already had 25 different variables that we were able to play with. And if you look at this now, so this is taken on a current version of MVAPICH on a test system. We now have over 400 performance variables that are present in that, and I think that's unprecedented. I think that's the most provided by any MPI implementation that I'm aware of, so we can actually start using these variables and gain that experience we just talked about. There's a lot of information for different collective operations. There's a lot of work on memory allocations that I think is very useful to see how much memory is actually used by MPI at what time. And so I think this is very useful. And again, this is the total list that MVAPICH provides right now. So you can, once you get the slides, feel free to zoom in. But there's actually also tools on that that actually just print out what you have on a particular system that you're working with. So I think that's a very good success story, and it was necessary to make tools work and to really show up what the MPIT interface can do. And with that, start this discussion we just talked about. What is the common thing that we need, and how can we move this forward? A couple examples of these counters, because those ones that was early in. So these things I think are very useful. Sizes of posted and unexpected receive queues. The memory part I think is very useful. These are kind of examples we did early on. These examples back from 2014, running the NAS benchmark with the number of entries in the receive queues and the unexpected queues. There's counters for min, max, and average. And you can kind of see in the unexpected part, as you scale a NAS, you actually have a spike in the unexpected receive queue. So that's something to potentially look at. We're worried about performance, because that also means there's a longer time to traverse this queue, and actually there would maybe some overhead associated with that. Memory allocation I think is very interesting as well. You can see how you scale as you go to large number process is even how much memory you're taking in the underlying system that's being taken away from your application. You can kind of see, for example, that in NEC 5000, one of the large codes of Argonne, you can kind of see a spike in the maximum memory allocation. So the average memory allocation is actually fine, but there's a couple nodes that actually have a large memory allocation. So that's something you should probably look into, which operations cause that, and either distribute it more across the system or change these operations so you don't have a lot of memory taken away from your application. And something very recent we're doing with a student right now, we're looking at doing a benchmark that stresses the message queue length. So that particular is designed to add packets into the unexpected message queue and add packets into the receive queues. And we're using MPIT out of the MVAPICH part to actually validate this benchmark. So this is very early work. We want to make the benchmark public once it's done. But you can kind of see we're able to show that as we scale up the number of nodes to kind of stress these queues, we also see the expected increase in these queue lengths. And so I think this has been very useful for that one as well to validate some of the models that we do on these systems. So this is what we currently MPI in the MPIT interface. As I said, we're currently extending the MPIT interface. The next one is called MPI Events, where we can do callback-driven performance analysis. So when an event happens, we can get a callback from the MPI implementation. We're doing this because PMPI does not provide this about the internal state, and MPIT does these aggregated, these start-stop events and what happens in between, but it doesn't give you access to individual events, it doesn't give you trace information. And so MPIT events is the idea. We do the same thing here that we did with MPIT for variables, but we do it for events. Again, we don't want to prescribe what MPI provides, but we want to basically give MPI an option to provide these callbacks. We can query them maybe we can work on that. There's a proposal that's particularly driven out of Jülich by Marc-André Hermanns. I guess the same idea, MPIT type information, so you query what's there, and then you can basically figure out what kind of semantics attached to that, and then you can set these callbacks. You can register these callbacks in the runtime. Whenever the event happens, you get a callback. You can either get them immediately, you can get them deferred, or you can even, if the event can't be handled by the implementation, it can be dropped. You can just be notified that it had to drop some events. Hopefully that won't be very often, but then but you would get the information and at least come out of that. So the reason why I bring this on, so you talked about challenges from the MVAPICH team. So I hope you can do the same thing you did with the MPIT variables, that we can also get MPIT events early into MVAPICH and to kind of start playing with this concept again. I think this could be a very strong addition to the tools part of the MPI as well. All right, so this is kind of on the roles of the open source project. I think that's really critical to get these implementations early in the hands of the users, to experiment, to also use the test vehicles before things are standardized to make sure the APIs that we have are right, so we can play with that and we can have prototypes. And then the last thing is, of course, we're living in changing worlds. There's changing landscapes in HPC. So I think we need to stay on top of that. And that's something perhaps that we haven't done often enough in the MPI standard, but I think that's something we need to pick up a little bit more on. We have new requirements, and I think we're starting to address them, but we've been criticized of not doing this enough, and I think that criticism was right, and so we're trying to catch up on that. So you look at these new application areas, there's the big data, deep learning AI area that is, I think, a good target for MPI as well. We started addressing this. The FP16 discussion is a starting point with that, so we have the right data model support in MPI for that. There's more and more discussion of using MPI for more than just HPC, to use more like distributed systems for communication systems, even server hardware. I think some of the companies that do server hardware are driving this. This requires some form of fault tolerance. If you think about a more distributed system, you don't have control over the whole job anymore. You actually need to have some more fault tolerance in there. So that drives some of the discussion about being able to live with a failure, being able to reason about the state of MPI after something happened, not tearing the whole thing down. So that's kind of where this discussion came from. We see new workflows like in situ processing, ensemble processing, scale bridging in HPC. That requires a much more agile and much more dynamic system underneath, much more dynamic runtime system. There's a concept called MPI sessions that we're trying to address this with. The idea is basically to get dynamic sets. You can grow and shrink these sets as needed. This is a very new concept. It'll probably take at least until MPI 5 to be fully implemented. But I think it's quite interesting. If you're interested in that, I'm happy to chat offline about this. And then also, how can we use MPI as a runtime for novel systems and tasking systems? How can it be a better runtime for things like Charm, for things like Legion, for things like OCR, where we actually need these more dynamic structures underneath? And so we're in discussion with those groups as well. Yeah?
So how do you envision sessions helping, is that in-situ visualization that you had up there?
Yeah, so the idea was, this early discussion, but the idea is you could actually have a session for your compute, and you could create a second session on the side of it that would carry the in situ visualization and the processing part, potentially even going outside of the compute partition. And then you could hook them up under one implementation at the end. But these are very early ideas, but the idea is that you basically isolate the compute from the in situ part, but have it under the same runtime system so they know each other and then they can communicate. Okay. That's kind of the core idea there.
And apart from the FP16, are there any other discussions over like deep learning in particular, or big data that's happening in the forum currently?
So I think also some of the more loosely coupled system ideas fit in it as well, because that's a much more loosely coupled structure that you're doing typically there. So this kind of connects to here. The main thing, particular for AI, is the FP16. And so we see also MPI is a very static one right now. The world is growing more dynamic, so we need some form of more malleability. We're working on that. The sessions could be, again, a gateway into that. But the main thing is, and I always want to stress this, MPI is not SPMD. Right? A lot of people associate MPI with SPMD. That's how we typically have programmed. That's what's easy to program in MPI, I understand that. but MPI can actually do much more. So we actually want to drive MPI to be supporting other things that are not as PMD, particularly towards the tasking systems, particularly towards these novel runtime systems. And then the last thing, again, very close to my heart with the tooling stack, we see a lot of the word tools becomes much more versatile these days. We're seeing a tool being fault tolerance management, a tool being power management, a tool being system monitoring. And so becoming the scenario where we want to have more of these tools run at the same time and composing these infrastructures. And so we have a QMPI effort in a way which was supposed to make this the work with the tooling interface. And also that, I'm happy to talk offline, but the idea is to be able to bring these monitoring systems into one single application. But with all these new ideas, I think one thing needs to be still upheld. MPI has always been standardizing the state of the art, things that are common, things that are agreed on. That's how MPI started, by looking at these different message passing parts. And I think we need to maintain that. If we just start standardizing research ideas, I think we're not going to have a stable standard. We want to have prototypes, we want to encourage experimentation, but it has to be ripe for the standard before it can actually go into the standard. That may be slower than some people would like, but I think it helps the MPI over the long run. So final thoughts, MPI standards, the standards are more than just writing the text. You have to make sure you address the right problem at the right time. You need to have the right functionality, talk to a user community, and actually grow the standard as needed. You need a very active, a large team to do this. Without these hundreds of people that are involved in that, that would not be possible. There's a lot of volunteer hours being invested in that. And you need to have a relatively defined process to make this work. And as I can't stress enough, we need these open source reference implementations like MVAPICH that show us what works, what doesn't work, that implemented, it gets in the hand of the users, are prototyping vehicles. This is really important to drive the standard. And I think with MPI, we cover these aspects very well. That's kind of, I think, why it has grown to the dominant standard in HPC. And we're continuing the evolution with MPI 4.0. That will be out very soon. If you want to have previews of that, let me know, and I can point you in the right direction. The MVAPICH project has been a crucial part of this process. That's why I'm very happy to be here and talk to you in this forum. It's a very good open source test platform. It was very quick in adopting new features and showcased the new features. And in particular for MPIT, it was really instrumental to show the capabilities we have in the standard. But of course, we need to stay aware of just the changing landscape, so it's not a done journey. So I think we have still a lot of work for us. MPI will continue to keep growing and evolving, and it'll be fun to do this together with the MVAPICH team over the next probably decades at this point. So with that, thank you very much, and I'm happy to take questions.